Hello everyone, I'm back again with another tutorial. In this video, we will explore how to read real-time clock data using the Zynq-7000 SoC on the Zybo development board. We will walk through the basic concepts, the hardware setup, and the key steps required to access RTC information reliably within an embedded system. This topic is especially important for applications that require accurate timekeeping, scheduling, or time stamping. Don't forget to visit my YouTube channel and subscribe for access to more in-depth tutorial and technical videos on SoC design. Before I directly go to the steps that are required for the project, I want to review the I2C protocol. I2C or I²C protocol is the abbreviation for Integrated Circuit Protocol, which is a synchronous communication interface in which a master device initiates communication with a slave device. It follows a master-slave architecture where the master generates the clock signal, thereby defining the data transfer rate or clock frequency. I2C actually is a bidirectional bus allowing the master to both write data to and read data from the slave. It's also a serial communication protocol, meaning that data is transferred bit by bit in synchronization with the clock. Communication over the I2C bus is achieved using only two lines. It is depicted in this picture that these two line names SCL and STA. SCL is serial clock line and SCA is serial data line. The I2C bus is widely used for low-speed communication in digital systems. Both SDA and SCL lines of I2C must be pulled up to the supply voltage, typically 5 volt or 3.3 volt, using low-value pull-up resistors, commonly around 2.2 kilo ohm. The open drain configuration allows any node on the bus to act as a master and safely drive the bus without causing contentions, enabling support for multiple slaves and multiple masters. And also, due to the open drain signaling and the presence of multiple nodes on the bus, the physical data transmission mechanism limits the achievable bus speed. In the next slide, it categorizes the different speeds that are used for I2C protocol. Standard mode, fast mode plus, highest speed mode, and ultra fast mode are 5 categories for this protocol, which range from 100 kHz up to 5 MHz. Communication between 100 kHz and 1 MHz is very similar in terms of implementation. However, highest speed mode at 3.4 MHz require additional design consideration, and ultra fast mode at 5 MHz also is unidirectional and even more complex. For this reason, standard mode, fast mode, and fast mode plus are by far the most commonly used I2C speeds, as they are the easiest to implement. Regardless of the bit rate, the effective data throughput is lower because the I2C protocol introduces some overhead, the transmission of address information and acknowledge bits. In addition to data consumes part of the available bit times. This protocol has some advantages: simple two-wire interface, multi-master and multi-slave support, address-based device selection, open drain signaling for safe bus sharing, low hardware overhead, well suited for lowest speed peripherals, wide industry adoption. On the I2C bus, any node can act as a master by pulling the SDA line low while SCL is high to start communication. Before transmitting, the master checks that SCA is high to avoid conflict with other devices. If another node is driving the bus, the current transaction is aborted and read-write later. Data bits are sent by changing SDA only when SCL is low, pulling SDA low for a 0 and letting it float high for a 1. The master then toggle SCL, giving the slave time to read each bit before moving to the next, ensuring reliable communication. Under I2C, the master first sends 8-bit consisting of a 7-bit slave address and a read-write bit. If a device with that address exists, it pulls SDA low to send an acknowledge. Otherwise, SDA stays high. This is the signal for read or write, and as you could see, for read, the master receives the data and it should be 1, and for write, it should be 0, and the master sends the data to the slave. And these are the acknowledge bit, which is 0 for successful transfer or 1 if receiver cannot accept data. After the acknowledge, the master either writes data to the slave or read data from it, driving SCL at the correct frequency. During a write, the slave sends an acknowledge after every byte, and if it sends a logic 1 instead, the master stops the transaction. On the other hand, during a read, the slave pauses after each byte, and the master must acknowledge receipt with an ACK, with sending this ACK signal. Actually, the master can send or receive any number of bytes, with each device defining its own message format, often starting with a header followed by data. And finally, at the end of a message, the master sends a stop bit, which is shown in this figure, by pulling SDA low, letting SCL go high, and then releasing SDA, which frees the bus for another master to start a new transaction. Alternatively, the master can issue a repeated start without releasing the bus by briefly setting SDA high, letting SCL go high, and then pulling SDA low again. The DS1307 RTC module is used in this project. At the heart of this module is the DS1307 RTC chip from Maxim, a low-cost yet highly accurate real-time clock that communicates with the Zynq-7000 processing system via I²C protocol. It tracks seconds, minutes, hours, days, dates, months, and years, supporting both 12-hour and 24-hour formats with an AM/PM indicator. The DS1307 automatically adjusts for months with fewer than 31 days and even accounts for leap year up to 2100. It also features a programmable SQW pin that can output square waves at 1 Hz, 4 kHz, 8 kHz, or 32 kHz. And also the chip relies on an external 32 kHz crystal, which is shown in this figure, which may drift slightly with temperature, leading to a potential clock error of about 2 minutes per month. This chip also has some other features. For example, it includes a battery input that allows it to keep accurate time even when the main power is disconnected. Actually, an internal power sensing circuit automatically switches to a backup supply during a power outage. The board actually has a 20 millimeter 3-volt coin cell battery holder compatible with a CR2032 battery, which at 300 nanoampere current draw can power the RTC for over 17 years. In addition, the module features a 32 kilobit AT24C32E2P ROM for non-volatile data storage capable of up to 1 million write cycle and communicating via the same I2C bus with address 50 hexadecimal. And also it has another hidden feature, which is support for the DS18B20, which is shown in this picture. This part is the 3 mounting holes near the battery holder for soldering this sensor. Okay, in the next step, I want to explain different steps that are required to complete the project for reading RTC data in Vivado. First, I have created a new project with the name of RTC I²C, and then I have to go and create a new block design. In the created block design, I will add IP, and the first and only IP that is required for this project is Zynq-7000 PS or processing system. Then I have to run block automation. Okay. Then I have to double click on this. In the PSPL configuration in AXI non-secure enablement, GP master AXI interface, I have to uncheck this option in order to omit this master AXI GP0 interface because we don't need it in this project. Then go to peripheral IO pins. Because we want to use I2C, you have to enable I2C 0 and then enable this. Because the Zynq-7000 on the Zybo board is connected to MIO 10 and enable for I2C 0 based on its datasheet. So you should confirm this, and all the setup for this block design has been completed now. Then go and right click on the block design and create HT wrapper. Then in the fellow navigator, you should go and generate a bit stream. It takes time. I will pause the video and we'll be back after generate bit stream become completed. Okay, now the bit stream generation is complete. You should cancel this pop-up window and then go to File menu, Export Hardware. Don't forget to include bit stream, then confirm this page. Again, go to the File menu, this time choose Launch SDK. In order to launch the SDK, the SDK program will be open and you could write the main code that is required for programming the SoC. Okay, in SDK, whenever it opens, you have to go to the File menu again, New Application Project to create a new application project. And I will choose a name for that, RTC Test. As you could see, alongside the generating a new application project, a new board stopper package will also be generated. Next, and I will choose MPT application. As you could see, two folders have been generated here, RTC test and RTC test board stopper package. One of them is for application project and another one is for board stopper package. So then I have to go directly to write the required C code for completing the project. Okay, in the next step, I will go to the RTC test application project and the SRC. I will right click and create a new folder here with the name of I2C. I want to generate two new files, one source file and another header file. For defining all the functions that are required for initializing the I2C and also the other functions that are required for reading and writing to this I2C. the header file. First, I will add the required header file in the PSI2C.h. First, I will include the site printf. Then I will include this header file that I already defined. Then I will write a function for writing data to this bus with a name of I2C register 8 write. First, you have to define a pointer to the I2C. Then this pointer actually selects which I2C controller is used. Then you have to define the I2C slave device address. The next parameters is 8-bit internal register address of the device. And then the data byte that is written to the register. Okay, I will go to the main part of the function. First of all, I will define the status, the type of integer. The return value of this function will go to the status variable that has been defined here. Send buffer with 2 bytes. Send buffer 0. Will be address, and send buffer 1 will be data. In the next part, we want to define the value for the status. We'll add the instance pointer here. The send buffer, and then the number of byte, and the I2C address. Okay, and then in the while loop, I will check to see the I2C is still busy. And then return a status. Okay, and then I have to define the first line of this function in the header file. Oh, there is related to this comma here, and also it has been removed here. It should also be capital. Okay, it's finished. If I want to do it for a 2-byte address, I could copy and paste it here, but it needs to apply some changes. For example, I have to change it to 16. This send buffer should be 3-byte. And here I have to define 0, 1, and this one 2. The 0, for the 0, I have to shift the address by 8. And then also this should be 3-byte. I will also, for another change, I have to change this to unsigned short. Okay, these two 1-byte and 2-byte address write function has been finished. I will go to write the required function for reading data from this I2C over this I2C protocol actually. Okay, for that I will copy the first line of this function and then write it here between these two. Okay, and I will change it to read. The return value will be a character. There is no need for defining the data. Then I will define two variables, write data and read data. Then store the register data, the register address that needs to be sent in the write data. Master send pulled, this one. The instance pointer should be as the first parameter inserted here, and then the address of this write data. One, and the I2C address. Okay. I have to use another function which is master receives pulled. Again, I will complete this with instance pointer, the address of read data, and again 1, and I2C address. Okay, and this function also reads 1 byte from the slave. Again, in a while loop, I have to wait until the I2C bus is ready and then return the read data. And finished. For completing the other part of the code for a function for reading with 2-byte address, I will copy and paste the reading function for 1 byte, and I will apply some changes. First, I will change it to 16. Again, the address, I will change it to unsigned short. This one. And then instead of write data, I will define a new buffer. And instead of this, I will use send buffer. And this one is 2 byte. And there is no need to apply other changes. The other part of the code is the same as 1 byte address. Okay, and in the next part of the code, I have to define a function for initialization of the I2C. I will give a name to this. I will define it as I2C init, and the pointer to this I2C controller, and then the device ID and the clock rate should be defined here. Okay, first declare a pointer to an I2C config, which is a structure contains hardware configuration information for the I2C controller. Then define the status variable that is used to store the return status of driver function. Then in another part of the code, use config in order to look up the I2C configuration that matches the device ID, the inter device ID of this function. And then in an if statement, it will check whether the configuration lookup failed. None means no matching device was found, and then prints an error message to the console, this error message. And finally, exit the function and report initialization failure. In the next part of the code, we will use the CFG initialized function in order to initialize the I2C driver instance. This I2C is the pointer to the AXI I²C instance, the one that is defined in the input of the function, and also the config, which is the hardware configuration, and this one is the base address of the I2C register. In the if statement, it will check if initialization was unsuccessful, and if it was unsuccessful, it will print the error here and then return the failure. Then in another part of the code, with set clock function, we could set the I2C serial clock frequency. In another part of the code, in a while statement, it will wait until the I2C bus become idle, and finally it will return the success. Then I have to go to the header file and add the first line of the other function here. So both of them are ready for use in the final main.c code. Okay, in the next step, Again, I will create another .c and .h file with the name of RTC.c and RTC.h. This RTC.c is for defining new simple wrapper functions that make reading and writing RTC register easier without specifying the I2C address each time. I will explain it later how it works and how it could make it easier. First, I will add the required header file. For example, the rtc.h and the I2C.h and then xparameters.h and also the psi2c.h file that we previously defined. I will define another two functions, RTC read and RTC write. The RTC read reads 1 byte from an RTC register at I2C address 68, which is defined here. As you could see, the I2C register 8 read function that we previously defined in ps_I2C.c code will be called here. And then for RTC write is also I2C register 8 write will be called, and the address of 68, which is the slave address of this RTC module, will be provided to this. And this one is actually for writing 1 byte to an RTC register at I2C address 68. Okay, we will save this and then go to rtc.h and complete this file for adding the first line of this two function. This one should be added here, and also this one. And the required header file. Okay. Since these three header file have been defined in the rtc.h, if you omit these three here, since this rtc.h is included in this function, there won't be any problem. So I could delete them to simplify the code. In the next step, I will go and generate another file, which is the main file that I want to use all the functions that has been defined until now in that to complete the whole main function for this project. Okay, I will choose the name main.c for that. Then first I will include all the required library. The stdio is the first one. Then xparameters.h. Then Zybo. And then RTC. And then I will define RTC second. For the register offset of the RTC second, and also I will do the same for the minute, hour, day, and the others. Okay, in the next part of the code, I have to define an instance of the Xilinx PS I2C controller with the name of RTC I2C, and then I will define two buffers for reading and writing, 7-byte RTC registers, complete this write buffer, and I also give an initial value to this write buffer. I have to also correct this part. Okay, in the next part, I will also define a new variable with the name of time for storing the time value, and then directly go to the main function. Again, in the main function, I will define two other variables. And then initialize the I2C. The device ID and the 100 kilohertz for the clock frequency. In the next part, I will read the value of the RTC control. And then clear all the bits except the fourth bit of that by line of the code. Using the RTC write, again, I will write back configuration to this RTC control register. So for that, I'm again using RTC I2C, and then this RTC schedule and control, and then the read buffer 0 this time, or with the certain. I will explain why we are using these two values. First, we will clear all the bits except the fifths of them, and then by doing this, we will again reset the 0 and first bits of this RTC control. If I go back to the slides, this is the control register. As you could see in the define, I defined this value for the register offset of the RTC control, and then as you could see, it has some special configuration. There are RS0 and RS1 for the 0 and first bit, and SQWE is the fourth bit of this register. And then if you go to the second slide, you could see that by giving 1 to RS0 and RS1, and also at the same time giving 1 to the SQWE. Here, the output frequency of the waveform at this SQW pin will be 32.768 kilohertz. So all this configuration and setup is to target this output frequency at this SQW pin. In the next part of the code, I will read the value of the I2C RTC register offset of the second. In a while loop, I will check to see if the 8 bits of this register is equal to 1 or not. This means that the RTC has been halted, and if that happened, I have again to rewrite another value to this RTC second. In this while loop, I will do this procedure. In the next part, I will use a for loop. And in this for loop, I will preset the time to this RTC register. The value of this write buffer should be written here. In the next part, in a while loop, the data from the RTC should be read. The time 0 will be assigned to second mode. Again, in a for loop, all the read data will be formatted. We will do BCD to decimal conversion. And then finally return 0. We have to also add a if statement here and check the previous value of the second with the new value of time, and if they are different, it means that 1 second has passed, and after that we could print the new time here with a special format that is defined, and with the value of time 6, 5 until 0. So the program has finished here. The main.c code is complete, you have to save it. In the final, you have to do the final setup and connect the module to the Zybo board. As indicated in this figure, these are the various pin headers, PMOD, which are JA, JB, JC, JD, JE, and JF. And as you could see, the MIO10 and MIO11, the two port that we set in the beginning of the project for the I2C connection, based on the datasheet of this Zybo board, is connected to the PMOD JF, JF2, and JF3. So based on this, you should do the connection between the board and the RTC module. The connection is shown in this figure. As you could see, the first pin of the module is ground, the second is VCC, and the third is STA, and the fourth is SCL. The first one, the ground, is connected to the corresponding ground on the JF, and also the VCC to the VCC. But the JF2 is connected to the second port, which is MIO10, and JF3 to the third port, which is equivalent to the MIO11. And after this connection become completed, you should go to the run configuration in the SDK, and then doing all the run setup, including the beta stream pass and also PS initialization. And then by programming the SoC, you could see the result in the console of the SDK. As you could see, based on the preset time that you do in the code, the time will be started, and each second the time will be increased. I hope you could use this video and it was helpful for you. In the final, again, I want to invite you to visit my YouTube channel and subscribe for access to more tutorial and technical videos on SoC design.